Hello, and thank you for being here. In this talk, we'll revisit two things: user registration and authentication. Uh, Everyone has written a web app at some point or something similar, and they are faced with a problem of how to register users and how to authenticate them. There are a lot of things in the landscape. There is 2FA, SSO, OAuth, OpenID Connect, everything. But almost always, none goes to the solutions. Everyone starts with the basic built-in authentication. Either they build something on their own, or they take something ready from their framework. Okay, and this is not bad. It's okay. But as you grow, problems become bigger, and you have to solve them. So the proposal, before we go to the proposal, sorry, let me introduce myself. I'm Vassilis Poursalidis. I'm a principal software engineer at Epignosis. Epignosis is the company behind Talent LMS, which is quite a big LMS system. So moving forward, in this presentation, I will introduce to you two protocols. The first protocol is proof of work. Most of you may know this because it's extensively used in Bitcoin. It didn't start this way, but was used there. Actually, it started as a mechanism to fence off spam email. And the second is zero knowledge password proofs. These are authentication mechanisms where you don't present the password to the other side, and you just prove that you know it. And those two will help us with the user registration, because on the first side, no password travels to the other side. And for the second part, the user authentication, well, actually, it's twofold. First of all, you don't send the password, and of course, you can rate limit what has been done. Okay, there are a lot of examples that we will see later. Okay, so how everything starts. You have a great idea, okay, but you have to implement it. And of course, solving user registration and authentication, it's not on your core domain. It's a supportive domain, so you have to go through it, make it happen, and go on. So you may want to do some rate limiting in order to fend off numerous requests, or you can use CAPTCHA in order to spot bots from humans. Or most often, do nothing. It's too early. I don't know if the idea will catch on. I'm not sure of everything, so I will not do anything at all, and I will think of it later. Because if the idea is successful, I will get more funding, I will get more developers, so I will be able to solve this problem. But if you do your built-in authentication, you have done your homework, you are confident, you don't store passwords in plain text, you solve them, and you store them like that. But again, as we will discuss, to me, this is not enough, because passwords get sent in your servers. And even though they travel through the internet unencrypted, at some point in time, SSL termination will cut this encryption. And from that point on, inside your infrastructure, it will travel as plain text. So first of all, let's meet our threat actor. We'll call him Elliot. He's able to do a lot of things. He's smart, he's tech savvy, and he's not an elite developer like you are, that you are developing. He's not an elite hacker. You are an elite developer, he's not an elite hacker. But his key point is the following. He has patience, he has a lot of time, and a single hack will pay his bills for months to come. So most of these people are from countries that the average wage is very low, and they keep hitting you. So is everything lost? No, everything is not lost. As always, this is a risk factor. You have to account for your risk. You have to know what your attacks are, and then justify what you will do in order for you to become more resilient. At the end of the day, hacks will happen. You have to accept that, and you have to defend for that. Okay. So let's meet our defenses. as I said previously, there are two protocols. The first protocol is called proof of work. This is to fend off attackers because we require an attacker to solve a puzzle, and this puzzle requires him to perform some work. This way, when a surge of requests come in, you are able to make the work harder and for him to slow him down. And you don't slow him down on the server side, you slow him down on the client side, on his machine. And based on the risk factors, you can increase or decrease this workload. So for example, if I am on a high risk factor, I get a lot of registrations suddenly, I can raise the risk factor, and then I can immediately see a drop in registrations. If this is distributed, I will not see a drop in registrations. But if this is from a single actor, then the registrations will drop. And I can easily spot out if this is an attack or not. Or if I hit Y Combinator and everyone is registering. The second thing is zero knowledge password proofs. We create a password verifier on the client side using the password. We send this to the server, and then the server proves, and then with the server, we communicate and prove to him that we have the password. And as a byproduct of this is that we can create session keys. So in order to do other crypto stuff while I am logged in. Now, let's first talk about rate limiting. So there are, as the name suggests, a form of cryptographic proof. Okay, these are called a little bit like client puzzles. You can think of them that you present him with a puzzle and then you ask him to solve it. For you, it's easy to detect that it's solved, but for him, in order to solve it, you have to put a lot of effort. Okay, and as you get the verification result, you can be certain that an amount of CPU or memory or network has been expended. It depends on the puzzle. Some puzzles require CPU, some puzzles require memory, and some puzzles require a lot of bandwidth. Okay. As I said previously, the protocol must be adaptive to both better computers. So I have more CPU, or I have a lot of machines, and also be able to adapt to the risk factor in order to make the work harder. And of course, we want to minimize this. The verification method has to be very quick. It has to be like one step. So here we have an analogy. We present to, let's say that you come to my house, and for everyone that wants to enter, I give you a Rubik's Cube. And every time you need to enter the house, you have to solve this. So if you try to rapidly go in and out, you have to solve it many times. So basically, I can fend off you. Someone that is a casual user will solve it and then get access to the service without any problem. And the reasoning here, not the reasoning, the analogy with the risk factor is that I can give you a 3x3 Rubik's Cube, or I can give you a 33x33 Rubik's Cube. Okay. So this is general how proof of work mechanisms work. Let me also say one more thing. Proof of work has been is gradually being phased out from cryptocurrencies because due to the problems that we had due to environmental impact of having to solve these hard CPU problems. But in our case, this does not apply. As I said, there is a minimum effort if you are a casual user, but you have to expend CPU, like pay money, if you try to create an attack. So these problems apply here, but not just as one-on-one. So let's go to a specific proof of work algorithm here. This proof of work is called Haskell. It was introduced in 2002, and the idea behind it that you get a data and you have to create your own nums, where you combine this data and then you pass them through a hash function. The number of leading zeros is the amount of work that you have to pay. For example, since this is almost randomly, the amount of leading zeros can fluctuate. In order to find the nums that can produce, let's say, 10 zeros at the beginning is very hard. You have to keep trying nonces. There are strategies on selecting a nonce. For example, I can do random, I can do a sequence, I can do both. But the idea is that due to probabilities, if I want 20 leading zeros, that is 1 in 2 in the 20th. So it's about 1 in a million as a result. So if the delta is low, getting leading zeros is quite fast. Like you will do 5-4 tries and you will succeed. But if the risk factor is big and the amount of the delta that you want is quite big, then it can take almost minutes. Also, the password originally used by Haskell was SHA-1. The algorithm being used, which is also against Haskell, is but in BBQing is SHA-256. And these are pluggable, of course. You can use whatever hash algorithm you want, as long as it is cryptographic secure. Now, let's see what a protocol, how it would work. So we have the application from one side and the service provider from the other. We can request a challenge, which is optional, and why it is optional, it can be piggybacked with other data as you exchange information with the server. So it isn't required, but if it's the first time you access the server, then it's not optional. Where you get back a JWT that contains a challenge and a delta. This JWT is signed and has a small expiration period, like for example, 5 minutes. Now, the application has to do the work and then respond with a JWT of its own. This does not have to be signed, but in order to contain the POW. For me, verifying this, the server, the service provider, is quite straightforward. It's like performing a single hash. But for the application, in order to perform this, as we said, it may be 1 in 1 million. Now, what are the best of all of this approach is the following, and we had a meetup, in the previous meetup where we discussed about accessibility. Since this is a machine-to-machine protocol, it's accessible by default because you don't present with the users anything. You use them to see that, and also machines can solve it. So your application not only can be user-facing, but also can be machine-facing. So let's see a small demo that I prepared. In this demo, it's not handshake with a server. It's just solving puzzles locally, but the idea is the same. So first of all, you will see that it will start with a lot of requests. I have my laptop unplugged at this stage, so it's not at full power. But then I plug it into power, and you can see there is a jump in the request per second because it has a boost in the CPU. Here it was a jump. And then you can see I increase the difficulty. Now difficulty is 7. What does it mean? It means that I want to have 7 0 bits. And as you can see, it could have like 400 requests per second. And as I increase the difficulty, the problem becomes exponentially worse. So I am able to lower the number of requests. Here we can see the number of requests. The next graph shows the average processing time, and it's calculated every 5 seconds. And the green is the number of timeouts. The number of timeouts, I have set the timeout at 6 seconds. If I'm not able to solve the puzzle at 6 seconds, then I give up. So as you see, as I increase the difficulty, the problem becomes exponential, and at some point it cannot solve it. Now it's difficulty 15. Okay, I will not continue. There is a small video that shows the timeouts, but it's okay. Yes, you can see that the request per second had dropped to almost 0. Yes.
Is there any green line over there?
Green line? No, the green was referring to this one.
Okay. Yeah.
So if you see, there was one timeout. Okay. Now, this is one of the protocols. Now, let's move on to the second one. The second one, as I said, is the zero-knowledge password proof. The idea behind these protocols is that I have cryptographic means where I can send you a verification function that is calculated based on my password. This password is stored on the server, and every time I present my username, the server can recall this verification function and then check what I have provided as proof with using this verification function, and can attest if I am allowed to access the service or not. As I said also previously, the good thing with PEG, which is the password authenticated key establishment, is that during this process, which is a form of zero-knowledge proof, is that we have a session key shared between the server and the client. For example, in order to give you a bit of context, all password managers like LastPass, like I don't know, 1Password or anyone else is using this kind of protocols. Your master password is never stored on their side. Using this protocol, you create an account, you send the proof, and they verify you. And using this bidirectional means, you also have session keys in order to perform other crypto, part of their protocol. Okay. Now, let's using the analogy that I used previously with the Rubik's Cube. The analogy here is as following. There is an illustration where you have to spot Waldo. There are like 1,000, 2,000, 5,000 people there, and you have to spot Waldo. We can think of this illustration as our password space, where all applicable passwords are different characters. And we've selected a single password, a single Waldo character in this illustration. Again, you come to my house and you have to provide proof that you know Waldo. From my point of view, I know also Waldo through the verification function. So you bring a large whiteboard that you have a pinhole in somewhere. You put the illustration and you put the large board on top of it. And you can show me, the whiteboard has to be approximately twice in size in order for me to not be able to infer where in the illustration you pointed. So I use this, and you can show it to me and tell me, no, look, there is Waldo. So I can you can provide proof that you know where Waldo is, and I can let you in the house without ever telling me where Waldo is inside the password domain. So let's see how this protocol works. Okay, as already we said, there is, okay, sorry. Let me introduce to you SRP6A. Okay, this is a PEG protocol. This protocol was implemented in Stanford. Unfortunately, all PEG protocols are heavily patented, all methods, everything. There are a lot of discussions both in the community and in IEEE because standards keep coming up that are rejected due to patent infringement. But this specific protocol was implemented in order to avoid any existing patents, any known patents, and it was implemented in Stanford as a part of a research project. Now, the good news is that it is throughout tested. There are a lot of available libraries already implementing this protocol for you to use, both on the client side and also on the server side. The bad news is that the protocol is not that strict when it was defined, so it's not enough IEEE specification that you can go by hand. So this means that different libraries have a few compatibility issues, but these are solvable. It's very easy, but you have to understand the protocol in order to solve them. And finally, it is a well-documented and well-deployed and well-tested protocol. There are other protocols like SRP6A, but they are either closed source or they have specific patents behind them and cannot be used freely. But there are some other free. It's not the only protocol. This is true. It's not the only protocol. So what we have seen, and there's a wrap-up, we have seen how we can use user authentication and user registration, take them in from built-in libraries that provide us with basic boilerplate, attach to protocols that are cryptographic, and enhance our solution. And what I mean enhance, by using proof of work, you can fend off dummy user registrations, you can fend off attacks throughout your API, and by using zero-knowledge password proofs, you can eliminate the transmission of passwords over the wire, and of course, you can have session keys shared among the two parties, cryptographic secure keys. Finally, one big thing that I would really like to discuss with you all, also after the presentation, is that we didn't cover at all how the risk factor is calculated. How do I map a risk factor and then apply this to a difficulty? This is a very interesting problem, and I'm thinking some things about it for the future. Now, I will be more than happy to take any questions, and then I can give the talk to Panos, who will discuss with us detecting threats at scale. Thank you.